This video is about synthetic division. It is a shortcut method of performing a long division with certain polynomials. It is used only when a polynomial is divided by a first-degree binomial of the form x minus k. Note that the coefficient of x is 1 here. The division process is simplified by omitting all variables and writing only coefficients, with 0 used to represent the coefficient of any missing terms. Since the coefficient of x in the divisor is always 1 in these divisions, it too can be omitted. These omissions simplify the problem. We'll see that using an example. Let's divide the following two polynomials. Note that the divisor is from the form x minus k. I'll write it on the side to see that x plus 2 can be expressed as x minus negative 2. So if we compare it to the common form or general form for the divisor, we'll see that k will be negative 2 for this case. When using synthetic division, we just write the value of k on the left side here. So I have to write, instead of x minus k, just negative 2. The numerical term of the divisor. Now, if we use a long division, we should write for the polynomial here, the whole polynomial, x to the third plus 7x squared plus 13x plus 6. But because this is synthetic division, we will use only the coefficient of each term. And if we see a missing power or missing term, then we'll replace it with its coefficient of 0. X to the third, its coefficient is 1. Next is x squared, its coefficient is 7. The x coefficient is 13. And next term is x to the power of 0, which is the numerical term, its coefficient is 6. Now we leave a little space and we draw a line and we start applying the algorithm. First, we bring down the coefficient of the highest degree term. In this case, it will be 1. Then we multiply the value of k, it's negative 2, by 1. The result is negative 1. We write it here. Then we add the two numbers, 7 and negative 2 is 5. K times this number, negative 2 times 5 is negative 10. We write the result in the next column, negative 10. We add the two numbers in this column, 13 minus 10 is just 3. Then we multiply k by this number, negative 2 times 3. We write the result here, it's negative 6. And after we add the numbers in the last column, we get 6 minus 0, 0. Let's see how to write the result now. 0 is the remainder. This is the coefficient of the numerical term. This is the coefficient of the first degree term. This is the coefficient of the second degree term. It's possible to write the result from right to left. So I can write plus 3. Then next number is 5. Next coefficient is 5. It will be the coefficient of the x term. And next one going to the left, we have a coefficient of 1 and it will be x to the second term. Or it's possible to see what will be the degree of the result polynomial of the quotient. We divide third degree polynomial by first degree polynomial, we should get a second degree polynomial. So this will be the coefficient of x squared plus 5, the coefficient of x, plus 3. And the remainder is 0. So if we divide the two polynomials, we'll get the quotient of x to the second plus 5x plus 3. And let's see one more example. Divide the following two polynomials. We can see that the divisor, the denominator, is x plus 3 and it could be expressed as x minus negative 3. So it is from the form x minus k. This means that we can apply synthetic division and the value of k for our case will be negative 3. We write this value just at the part of the divisor, only negative 3 here. Then we write the coefficients of the dividend, and we should be careful for missing terms. So the first term is 2x to the third, its coefficient is 2. Next one is 5x to the second, its coefficient is 2. We just write the coefficients. Next one is missing. We don't have an x term, so its coefficient should be 0. And the last one is 9. Then we leave some space and we draw a line and we bring down 2 below this line. Then you multiply k by the number for the first column below the line. Negative 3 times 2 is negative 6. We add 5 and negative 6. The result is negative 1. We multiply k by this number. Negative 3 times negative 1 is positive 3. We add the two numbers in this column. The result is 3. We multiply again k by this number. Negative 3 times 3 is 9. Negative 9. So 9 and minus 9, if you add them, we get 0. So this is the column for the remainder. The remainder is 0. Now we divide third degree polynomial by first degree polynomial. We should get the second degree polynomial. This is the coefficient of x squared, 2x to the second. Then minus 1 is the coefficient of x to the first, right? Minus x. Then 3 is the coefficient, the numerical term, plus 3, and the remainder is 0. That's the result. I put it again in the form dividend over divisor equals quotient, plus the remainder is 0. Note that we can always check our work. If we multiply 2x to the second minus x plus 3 by x plus 3, we should get the original polynomial. You can try to do this multiplication to make sure this is the correct result. One more example. Divide x to the third plus 8 by x minus 1. The divisor is from the form x minus k, and k will be 1 in this case. We write only the coefficients of the dividend. X to the third has coefficient of 1, then x to the second and x odd terms are missing, so we replace them with their coefficients, zeros. And then we bring down the last coefficient, 8. We leave some space. And then we have to bring down the first number, it is 1. We multiply k by this number 1. The result is 1. We write it here. We add 1 plus 0, the numbers in this column. The result is 1. Then we multiply k by this number. 1 times 1 is 1. We write it in the next column. We add the two numbers in this column. 0 and 1 is 1. 1 times 1 is 1. 1 and 8, 9. There's a remainder in this case. Let's see what will be the degree of the result polynomial. Third degree minus first degree will be second degree. So those are the coefficients of the second degree, the first degree term, and the numerical term. We have x to the second plus x plus 1. The result of dividing x to the third plus 8 by the divisor x minus 1 is the quotient. We take it from here, x to the second plus x plus 1 plus the remainder over the divisor. Well, you are familiar with this form without knowing it. For example, if we divide 9 by 2, we get a quotient of 4 and the remainder 1 over the divisor. So we have the same situation here. Dividend divided by the divisor equals the quotient plus the remainder over the divisor. If we multiply both sides of this equation by the least common denominator, x minus 1, we'll clear the denominators. So we get x to the third plus 8 is equal to x minus 1, the divisor, times the quotient, x to the second plus x plus 1, plus the remainder. The following theorem is a generalization of the illustrated division process. For any polynomial f of x and any complex number k, there exists a unique polynomial q of x and number r such that f of x will be a product of x minus k and qnx plus r. Suppose that we want to find f of k. This means that we have to substitute x with k into the function. So we'll get k minus k, and this factor will be 0 times q of x plus r. So we see from here that f of k will equal r. This provides the following remainder theorem, which gives a new method of evaluating polynomial functions. If the polynomial function f of x is divided by x minus k, then the remainder is equal to f of k. This is called the remainder theorem.